Hello class. So this is Thursday's lecture, and for today's lecture I really want to focus in on um, uh, uh, exponential functions and the types of exponential functions that we can have. So there are two types of exponential functions that we can have. There is compound exponential functions, and then there are compound continuous exponential functions. Okay, so if we're talking about just regular n compounding functions, then really what we're looking at is the following. So this is for n compounding. So for n compounding functions, let me just clean this up just a little bit. So n compounding. We're really looking at a particular type of function, in that we're looking at the function f of x is equal to a times 1 plus r over n, all this raised to the n times t. Here in this case, a is going to be the initial amount that we start with. R is going to be the percent at which the stuff that we start with, a, is going to grow at. And n is going to be the number of times we're going to compound this given stuff for a at a rate within a given year, and t is obviously in years. So typically, well, I guess a great example for just compounding interest would be annual compound interest. So let's suppose that we had an investment of $1,000. So let's suppose we had a is equal to 1,000, and we were investing it into an account that compounds annually. So compounded annually. At a rate of, I don't know, we'll say 0.2%, or better yet, let's just say 2%. Okay, so with all this information, we can actually plug in values into our n compounding interest or n compounding formula to really set up the formula to really answer questions of future value of either the initial population or our initial investment. In this case, it's an initial investment. So in putting this together with our formula, we know that we have f of x is equal to 1,000, which is our initial amount, which is what we said, a, times 1 plus r. But r in this case was given to us as a percentage. Whenever we plug these values into our formula, we really want to write them as a decimal. So this is going to be 0.02 divided by n. In this case, we're told that the number of times or how this amount is compounding is going to be annually. So we want to let n equal to 1, all raised to the n 1 times t. So now we've set up our formula. We want to simplify this a little bit to compound to determine the amount of in an account, if you will, where a $1,000 investment is made at a rate of 0.2% or 2%. At a rate of 2% compounded annually. So we could simplify this to 1,000 times 1.02, all raised to the t. So now we could ask such questions like, well, how much will be in the account after 10 years by simply plugging in 10 for our value of t here. And when we do that, as just an example, when we do that, we want to plug this in our calculator. So we get 1,000, so times 1.02, all raised to the 10th, for example. And so we can do this by evaluating f of 10. we do that, we get 1,000 times 1.02, all raised to the 10th, which is approximately equal to $1,218.99. So we could say approximately after 10 years, the worth in the account the value in the account will approximately be $1,218.99. Now, this, along with some of the other stuff that we've already worked on, will really help us in terms of solving for our values of time. If we were asked to, if we were tasked with determining how much will be how much time will have lapsed if our investment is equal to $10,000, for example. So we can flip this, right? We can, instead of giving us a time and finding out how much is in the account after that much time, we can actually flip this. We can look at we could look for determining time if the account is at a certain amount, say $2,000. So let's flip this and let's ask the following question. How much time, or better yet, how many years will it take for our investment to reach $2,000? Okay, so again, we're going to use the same formula as we used before, the same equation that we used before. So we have f of x is equal to 1,000 times 1.02, all raised to the t. So here, in the last example, we were given time and we were asked to find f of 10. Here, we're given f of x equal to 2,000 and we're asked to solve for t. So, plugging in known values, I have 2,000 is equal to 1,000 times 1.02, all raised to the t. So now we have to determine the value of time for when the investment has reached $2,000. So in other words, we need to isolate t and then solve for t. Well, the first thing that I can see in terms of solving for t is I notice that I have this constant, or this factor of 1,000 out in front of what appears to be 1,000 out in front of my exponential portion of my equation here. So I want to divide both sides by 1,000, which is the first thing I want to do. And in doing so, I get 1,000 divided by 2,000 divided by 1,000. That should be equal to 2. And then just rewriting what's remaining, 1.02, all raised to the t. So now at this point, we have to figure out how to get t out of the exponent here. And remember our properties of logs, our exponential properties of logs. In the previous lecture, we addressed that too, which says that if I have the log of b raised to the x, I could rewrite, or the log of base b of a raised to the x, I could rewrite that as x times the log of base b of a. So, but in order to do that, I have to take the log of the right-hand side of the equation, and of course, because we have equality here, I have to take the log of the left-hand side of the equation. So, we'll go ahead and do that. Take the log of the left-hand side, and that'll give me the log of base 2, or log of base 10 of 2 is equal to the log of 1.02, all raised to the t. Now, at this point, I could pull down the t out of the exponent and as a multiple of the 2, and I get the log of 2 is equal to t times the log of 1.02. Now, at this point, I could divide both sides by the log of 1.02. So I'll go ahead and do that. So I get the log of 1.02 divided by the log of 1.02. And I get t is equal to the log of 2 divided by the log of 1.02. Now, entering this in our calculators, we're going to approximate to the nearest year. So I have the log of 2 divided by the log of 1.02, which is going to be approximately 35. So what we can say then is that after 35 years, the amount that will, or actually let's put it this way, that the number of years that it would take for our account to grow to $2,000, given that we have an account that's compounded annually at an interest rate of 2%, is going to be 35 years. Now keep in mind, guys, the same type of properties that we used here will also apply to continuous exponential functions. Remember, in a previous lecture we talked about continuous exponential functions as f of x is equal to e raised to the x, which is probably the most simplest compounded continuous exponential function that we can think of. But these same properties, given that the same properties for logs that we've been talking about all week will apply for natural log and exponential functions, these properties will apply to them as well. Okay, so what I'm going to do is I'm going to do a lecture every day for the next week and a half. So you will get another lecture tomorrow for Friday. So expect to have another lecture in the discussion forums on Friday, on Saturday, and Sunday as well. So I'm going to do one each day that we're out. So because I don't want to break these up, I don't want to have these in hour and 40-minute chunks. I want to do them in little bits here and there, and I think that'll help out a lot better. So I don't know. Let me know what your thoughts are, and please, if you have any questions, please post them to the discussion forums, and we'll look into those. All right. Thanks, guys.